Hey, welcome back to your favorite Fundamentals of College math class. We're going to take a look at statistics in this unit, sampling frequency distributions, and some graphs. Here's our objectives. Let's start out with some vocabulary here. So first of all, statistics are this method of collecting, organizing, analyzing, and interpreting. So collecting, organizing, analyzing, and interpreting data as well as drawing conclusions. There's two types. There's your descriptive statistics. That's like the statistics that I give after the exams, your mean, your average, and your standard deviation or descriptive statistics, as well as the five-number summary with your maximum, minimum, first quartile, median, third quartile, right? Inferential statistics are statistics, whoops, that make generalizations, draw conclusions. Excuse me, sorry about that. For example, maybe you do a study and of a sample of CSN students or whatever, and you study their time spent on social media, and you can draw a conclusion. More time spent on social media means lower grades or whatever it is. Inferential statistics would be making generalizations, right? Having some sort of doing significance tests. A population is just simply the set containing all the people or objects whose properties are to be described and analyzed by the data collector. So you can do a study and you can actually sample everybody in the entire population, or if it's a study, let's say you're studying all the people in California and you're trying to just get a sample, you can realistically you can't contact everybody in California, let's say, so you take a sample instead, which is a subset or subgroup, and preferably a representative sample, not preferably, you should have a representative sample that truly represents the entire population. Okay, so for example, you have a group of hotel owners in a large city decide to conduct a survey among citizens of the city to discover their opinions about casino gambling. So what's the population? That's a set of all the citizens in this city, right? That's your population. All the citizens, sorry, in the city is your population. That's a whole population, right? B, one of the hotel owners suggests obtaining a sample by surveying. So they just want to survey all the people at six of the largest nightclubs in the city on a Saturday night. So instead of sampling the entire city, they think, hey, let's just do a sample, and then we'll ask them, um, these people at six of the largest nightclubs in the city. They'll be asked to express his or her opinion on casino gambling. Does this seem like a good idea? Well, the problem is this is not a representative sample. So it's really a poor idea because at the nightclub, you're probably going to have people that have a more positive attitude toward gambling, right? So it's not, again, it's not representative, um, of trying to figure out if their opinions about casino gambling for the entire city. All right, random sampling. This is a sample obtained in such a way that every element of the population has an equal chance of being selected. Okay, this is like a gold standard for trying to find a representative sample. So the methodology is to identify each element in the population, assign numbers, randomly select numbers, and assign the elements of the population who have those numbers to the sample set. Random sampling. Which of the following way is the best way to select a random sample to find out how the city's citizens feel about casino gambling? Or A, how about this one? Randomly survey people who live in the oceanfront condominiums in the city. Would that be representative? You say no, because a lot of these condominiums, you're going to have these. They lie along the oceanfront, right? So they're going to object to the increased traffic and the noise. Again, not everybody in the city has an equal chance. It's probably very touristy in that area as well. So not a good representative sample there. Is this a good way? B, is it a good way to select a random sample? B, survey the first 200 people whose names appear in the city's telephone directory. No, because again, it does not give each citizen an equal chance to be selected. So how about C? What if we randomly select neighborhoods of the city and then randomly survey people within the selected neighborhoods? Yes, everybody's got an equal chance there. Okay, you wanna randomize, right, the entire city. So that's one way of doing that is you randomize people within randomized areas, neighborhoods. All right, let's move into constructing a frequency distribution. So here's a frequency, here's some data for the age of maximum yearly growth. So the first person was age 12 when they had their maximum growth in a year. They were age 12. And if I'm going to make a frequency distribution. A frequency distribution is simply how many. So you notice on this left-hand side, we're gonna classify. Here's our classifying age of maximum growth. There was how many people, how many boys age 10? Looks like there was one boy age 10 who grew the most when they were 10 years old. How many age 11? Two age 11. How many age 12? Looks like five age 12. Anyways, we could keep going with this. And that's how you create a frequency distribution, is you just count them up. You say, how many of each one do I have? There it is. And there's 35 total numbers, by the way. Okay. But this is our frequency distribution. Now, if they were to ask, what are some of the conclusions you can draw from this example? So if you're looking at this, you're probably thinking, it looks like between like 12 and 15, in here, that's where most boys have their biggest growth in a year, right? And then more specifically, it looks like, the most boys out of these 35 boys, nine of them had most of their growth, the largest portion of their growth at age 14, right? So the number of boys who attain their maximum growth at a given age, it increases up until age 14, and after that, it decreases after that. All right, how about this one here? Let's do another frequency distribution. Here are the statistics test for a class of 40 students. Graph the frequencies into classes that are meaningful for the data. So if I was doing a frequency distribution here, if you're thinking about this, let's do classes. Since these are grades, I'm going to do, looks like my lowest here is a 47, 45. So we're going to go 40, 49, right? We'll do it by 10. Anything 50 to 59. And then we'll write the frequency of that. Who got D's in the 60 to 69 range? How many got C's 70 to 79 range? How many got B's? And how many got A's? All right. Then you just start going through this. You say, well, 40s, let's say I got 47. Any other 45, 43. Oh, 43 was our last one. 1, 2, 3. So it looks like we have 3 in there. How many in the 50s? 57, 54. Looks like there was 6 there. Anyways, we keep going with that, just like that, and I've got the frequency distribution right here. That's how many you have of each of those. All right, so we want to vary the width by 10, right? Because this we're talking about grades. Talking about grades. You know, if we would have had in the data something less than 40, you could have even said below 49, you know, in case there was somebody who got like a 30 or something, you know, and then you put the frequency on there. All right, histograms and frequency plots. So a histogram is a bar graph. That's where that frequency distribution comes into play. So it's a bar graph of bars that can be used to visually display the data. So this is, you remember the data from the boys' ages of maximum yearly growth. So there was one person, age 10, who achieved maximum yearly growth at age 10. There were 2 people, right? So it goes up to the 2-year mark. 11. You remember there was the most was 19, was 9, age 14. So it goes clear up. See that to age 9 there. That's how you create those. So you take that frequency distribution and create a bar graph with that. You know, you could do the same thing with our data over here. And you could have, you know, for those, so you could have a 40 to 49 bar graph, and there's 3 people, right? So this goes up to the 3, and then you have 50 to 59, and there's, didn't do this very good here, but 6, and so on, right? You can create a bar graph. Now I should not have space between them. Notice these don't have space. I just can't do this very good on my pad here. All right, now frequency polygon, the only difference is you take the middle of each of these bar graphs here and you just connect the dots. Connect it right to the middle. And then you can actually see that all through there. And you can forget about the bar graph. So that's a frequency polygon. And it's just kind of showing you, it's just a visual way of displaying the data is all a histogram and frequency polygon do. Okay. Stem and leaf plot is another way to look at the data and kind of display that. So your stem consists of the tens, the leaf consists of the units, digit, typically speaking. So here, for example, if you've got this data for a stem and leaf plot, looks like our lowest one here is like 43, right? This is from the data for their scores. So we have, here's my 40s. Let me do them first. 47, 45, 43. So my stem are the tens, my leaves are the ones. So 47 is displayed like that. Now I'm done with 47. Now I've got 45. So 45, and I just put it there. That's representing 45 right there. Now I've got 43. So 43, right? That's representing 43. So 47, 45, 43, right? And then you go to your 50s. Then you go, all right, I got a 57, so 57. Looks like I got a 54. Looks like I got a 56. I got 57. I got 59. Whoops, I missed a 50. I have a 50 first, and then I have a 59. And then when you rewrite the data, if you want to, you can put them in order. So, you know, it'd be 43, 45, 47, and then be 50, and be 53, 54, 56, 57, 57, 59, but it doesn't matter, right? Either of those is fine. But here's your whole stem and leaf plot here. So you're all done with all the data, and then that displays all the data for you. It's nice because you're like, hey, I got a whole bunch of these in the 70s. Right? You can see that from your stem and leaf plot. You can kind of see that frequency distribution a little bit. Now, deceptions in visual displays of data. This is kind of, I love this as part of this section because the old quote, it reminds me of the old quote. There's three kinds of lies: lies, damn lies, and statistics. An anonymous quote. But it describes the persuasive power that numbers really have, particularly how statistics are used to bolster weak arguments sometimes. You see this all the time with politicians and during debates and so on. I'm sure we'll see it during the next presidential debate and so on. So you want to look carefully at your data, right? So here's some examples here. Graphs can be used, it says, to distort the underlying data. So if you look at this, this is all of these are showing the same data, the poverty rate. So in 2001, the poverty rate was 11.7%, 2002, 12.1, 2003, 12.5, and so on, right? And here it is displayed. It's displayed here, and then they also displayed it over here. It's the same data plotted. What's the difference? Well, you can see how they stretch this scale out a lot more than over here. This is a little more compressed scale, right? So depending on the argument you want to make, right? If you stretch this out, you're like, oh my gosh, this is really the poverty rate's really increasing, right? It's really increasing. Well, it's not really showing that over here. Again, depending on that scale, but so your horizontal scale, depending on that compression in here, can really help you bolster an argument potentially, right? Like you don't want to be deceptive in your visual displays of data. You try not to be deceptive, right? You're just displaying the data. This is what it is. Don't try and be deceptive with it. So when you're things you want to watch for in these is there a title, right? Is everything labeled, right? What's the title here on my vertical? And then what's my title over here on my horizontal, right? I think I said that wrong over here. I'm sorry. This is our vertical. This is our horizontal. Are the numbers lined up with tick marks? So it's clearly indicated, right? And spaced out appropriately. It's not going like 1, 2, 10, 20 or something, right? Like 1, 2, 3. If you're going by one, this should be consistent. Do the design or cosmetic effects draw attention from or distort the data somehow? That's something you want to think about. Again, it should be equally spaced intervals on each axis, both the horizontal and the vertical. Bar sizes scale proportionately. Is there a source? Where's your data actually come from, right? And was it from an entire population or a sample? How did you sample? Was it a representative sample, right? So these are all things you kind of want to think about when you're looking at your data. So here's an example of some misleading visual displays. So here you notice in 1980, the number of square feet in an average U.S. home was 1740. In 1990, it was 2080. And then in 2010, it was 2,392, the number of square feet in an average U.S. single family home. But the problem here is these widths are changing so dramatically, right? This only went up from 1740 2080. It went up 340, but it looks like it went up a lot more from here to here because of the width, right? This width got so much bigger on this height, right? It doesn't really look proportional, whereas it only increased, 312 square feet from 1990 to 2010, right? Plus, This is from 1980 to 1990. That's a 10-year difference, but from 1990 to 2010, that's a 20-year difference too, right? So they should show the next year they should show is the year 2000. They don't, right? So, anyways, you can very easy to accidentally mislead with visual displays. So go ahead and kind of watch that as you're going through things. Thanks so much for listening. We'll see you next time.